In this video I will show how I try to understand the origin of sideband noise in this selective amplifier. At the moment it is running as an oscillator. Here is the input and here is an output which is amplitude limited by crossed diode 1N4148 in series, two such units. So here is the block diagram and a connection from this output, the limited one, to the input brings the unit to an oscillator. Here is the signal analyzer window of Linrad. It has been running for a very long time, 1.1 million averages over 85 hours. I have been doing other things, so I have collected far more than necessary. Anyway, this is the result of the 1 watt oscillator I just showed. And the upper trace, which is white in color, that's the amplitude noise. And the yellow trace is the phase noise. The frequency scale, 200 Hz here. It's this peak, overtone from 50 Hz, so that is 200 Hz, 100 Hz, 50 Hz. Note that 50 Hz is almost only phase noise, phase modulation. 100 Hz, and this I don't know what it is. And then here is 700 Hz. That is the DC, because I'm using two direct conversion receivers, and here is the center, which is 0, and here is the carrier at 700 Hz, and here is the mirror image, and here is 1400 Hz. It's the double this frequency. Probably from the mixers, because there are 20 megahertz overtones generated internally in the mixers. Anyway, they give this peak at 700, which is totally uninteresting, and it is surrounded by 50 Hz, 100 Hz, 150, mainly odd overtones, 250, 350, 450, and then it coincides with the 50 Hz overtones. I will take down the numbers for these curves, and I do that by changing the scale here, dB. I go from 5 to 1, and then I have to shift vertically the carrier position to, let's say, 140. And here I can read the value at 50 Hz. It's here for the amplitude noise, and at this point for the phase noise. And I will make a little table about the information I have here. These curves show the sum of the squares of the real part and the imaginary part of the correlation spectrum. Now, that is not quite what one should show, but it could be safe to show it. So I click now in this box here to show for the phase noise here. This a little bit unstable. That is the raw data into the correlator. That is the detected FM signal, which then is used to compute correlation between the green and the red trace. And that you can see here at very low frequencies, the dominating noise is from the receiver itself. Oops! Did you see that? And then it goes down. It's this glitch. These glitches occur now and then, and they explain a significant fraction of the total correlation noise. So I will come back to that. The red dots, that is the imaginary part. Adding this into the total, which is, the yellow is the real part when it is positive. Blue is when it is negative. The sidebands of 50 Hertz on the DC components happen to come out with a negative sign, so you can see it comes also here. The imaginary part, which should ideally be 0, is far below the real part, all the way until about here, where the result is no longer significant because of the proximity to the 0. Now I look at the same for the amplitude noise. That's here. And this is far more striking because the average correlation is higher than the signal itself. And that is, of course, an artifact of some kind. And you can see here, I had these glitches here and here and here. And there will come more, and I will wait for one of the glitches to come. I look at the baseband waterfall and wait for one more of these narrow band noise bursts to occur. It's not really a glitch, it's a narrow band there. And here you can see how the signal goes up high above. And now it's back again, because this spectrum here is the average of 10 spectra. So the first problem with my oscillator is, what is the origin of these narrow band noise bursts? Is it the crystals or is it in the amplifier? To find out, I will use the unit as an amplifier, amplifying a good oscillator. I will use this oscillator from Wenzel and run it through this oscillator configured as an amplifier. And then I can study what will happen at the different stages within this amplifier. But first I look at the correlation spectrum of the oscillator itself. Already after 10 seconds, I can see here it is much better. At 50 Hertz, the amplitude noise is minus 162 or something. And I had before minus 148. So there is a dramatic difference. I don't have to wait for a very long time to get this accurately enough, because it just has to be significantly better. Already after 1 hour and 15,000 averages, the result is accurate enough. As I can see from the position of the imaginary part, it is about 10 dB below the real part at 50 Hertz, and it's better at higher offset frequencies. And this is the phase noise. And I look at the amplitude noise, and here it is even better. So I can take these curves and use to read the sideband noise at different frequencies for this oscillator. So here is my table. The amplitude noise of the Wenzel minus 162 is much lower than for the oscillator, my home built thing, at minus 148. That is at 50 Hertz. At wider frequency separations, the difference becomes smaller, and at 400 Hertz, the difference is very small. For the phase noise here, at 50 Hertz, the Wenzel is 7 dB better. At 100 Hertz, it's only about 1 dB better. At 150 Hertz, my oscillator is better than the Wenzel oscillator. So this is something to remember. I am now running my oscillator as an amplifier. There are still glitches and I wait for one of them to come. There we had. So you can see glitches are still very important. I will leave this running for some time. The power is still 1 watt and I'm feeding the full power of the Wenzel into the amplifier. And I still have 15 decibels attenuation on the output. And the signal level is very closely the same as I had when it was an oscillator. 4 hours as an amplifier at an output power of 1 watt. There are these narrow band noise bursts also when the unit is running as an amplifier. As you can see here, the spectrum looks similar to before. I will evaluate the AM and the phase noise from the relevant spectrum. And here is phase noise, and it is clear that up here somewhere the distance from the real part to the imaginary part is getting small. So the curve is a little bit noisy. But I'm not going higher than 400 Hertz, and 400 Hertz, this is okay. And also 50 Hertz. And I look at the AM noise here, and it is even better. As an oscillator or as an amplifier, at close range, the oscillator is more noisy than the amplifier, but the amplifier is much more noisy than the driving low noise oscillator. At wide separations, the amplifier output is the same, regardless whether it is an oscillator or an amplifier. And this is valid all the way to about 200 Hertz separation, maybe 150, for amplitude noise. For phase noise, it is similar. Best is the driving Wenzel oscillator when running it directly to the analyzing system. But when the amplifier is used as an amplifier, it is better as compared when it's used as an oscillator. Differs by 3 dB. But already at 150 Hertz offset, it is the same regardless whether it's an oscillator or an amplifier. And the low noise oscillator from Wenzel is clearly noisier than this selective amplifier at separations above 150 Hertz or so. But the dominating problem is these bursts of close range sideband noise, and they come all the time. I have inserted 10 dB of attenuation on the input and also reduced the attenuation on the output by 10 dB. So now the oscillator amplifier gives 100 milliwatts at the output, and glitches are still, narrow band noise pulses are still present. You can see one here. They seem to occur less frequently though. And I will read the values from these curves and take down on my note sheet. Now I'm running as an amplifier at full power, but I have replaced the power supply. there are still problems with these narrow band noise bursts, but I can see that the noise is a little bit lower. And I will take down notes from this, but first I will demonstrate what we have. Here is phase noise, and it looks reasonable. You can see how the green and the red direct the results of the... Oh, there we had one of the glitches, and now it's back. And this was phase modulation. And here is AM modulation, and you can see that there was another glitch or noise burst. So the data between these noise bursts is much better than the reading I can get out here, which is about 152 or 153. And that is still quite good at 50 Hertz. 152. That's about the same I had before. Now I clear the average correlation like this. Oops, there we had a glitch, so I have to clear it again. And then I can see that if I wait for a while, I leave the camera running. And at this point we are at minus 153 for the AM noise. And it's approaching minus 154 at 50 Hertz. And there has not yet been any noise burst. Oops. So I was down at minus 154.5. And the data I have collected at 50 Hertz, the best was 152.5, but that was at reduced power. At full power I had minus 152. So these noise bursts are very important, and I have to find out where they originate. It's not from the power supply anyway. I have now disconnected the power amplifier and I'm using only the crystals and the pre-amplifier in this selective amplifier of mine, and it's already clear this is much better. I have amplitude noise at 158, phase noise 156. And that is after 1 minute 20 seconds. So statistics is not yet very good. Here is the phase noise, and you can see that the imaginary part is very near the real part. I have to wait. And for amplitude noise, it's already better. So this is the value I have, because the imaginary part is already about 10 dB below. But the trace is very noisy, and it will look better tomorrow. Here is the preamplifier. Input here through a capacitor, and there is also a resistor on 100 ohms to ground. This capacitor is tuned for the impedance here to be exactly 50 ohms on the center frequency. 20 crystals in parallel, tuned with this capacitor and also these two for resonance on 10 megahertz. This voltage divider gives a reduced voltage to the gate of 6 parallel J310, and they have all separate resistors in the source, decoupled, to make the current the same through all transistors. And then the output comes here. The impedance is 9 ohms, but it cannot even be loaded by 50 ohms because the current capability is not big enough. It will go nonlinear. The capacitances of the transistor, they are balanced. First, there is the signal from the source is phase reversed by this transformer, and then there is a series filter here to make sure that only the 10 megahertz signal passes, so we don't get oscillations far from the desired frequency. And then there is a resistor and a capacitor, and also this inductor. This allows me to set the phase exactly right, which means that the capacitance between the gate and the source is not present anymore. And a similar thing is done for the collector. And I think this connection is called bootstrap, an emitter follower that makes the voltage on the drain follow the voltage of the source. So the impedance here becomes very high. Here is the experiment you have just seen. The Wenzel through the Pre-Amplifier, and then output is taken through a capacitor and a voltage divider with 100 ohms resistors. It means that the impedance here will be about 50 ohms. The gain from here to here is about -1 dB. And the power amplifier just a grounded input to keep the DC through this amplifier very small. This will be the next experiment. This inductor will supply the normal bias voltage for the power amplifier, and I feed the Wenzel oscillator directly in here. The limited output is terminated in 50 ohms, and the output is attenuated by 15 dB to give the normal level to the analyzer. Here is the power amplifier. Here is the result for the power amplifier after nearly 2 hours. It is quite unexpected. There are no narrowband noise bursts, and the phase noise and the AM noise are fairly low. I will read these values, but first demonstrate what the full information is. Here you can see for phase noise the imaginary part is far below the real part, so the yellow curve here is accurate. For AM noise also. So I can read the data from these curves and compare with the result of the Wenzel oscillator without any amplifier. What I can see is that the phase noise here, -156.4, is very close to the phase noise of the Wenzel oscillator at -157.2. I don't think this decimal is very significant, but if I go to 100 Hz, I get 160.0 and 159.9, and so on. The numbers are the same that I observe now and that I observed on the Wenzel. It differs here by 0.4 dB in the other direction. If I look at amplitude noise, it's different. The Wenzel is at -162, while the power amplifier is at -156. That's a degradation by 6 dB. Not very much, but significant. At 100 Hz there is also a degradation from 159 to 165. That's also 6 dB. And going to, let's say, 300 Hz here, it's minus 166 for the Wenzel and minus 163.9 with the power amplifier. And this means I have flicker noise, amplitude noise in this amplifier. Sideband noise in this power amplifier could be introduced because there would be present some low frequency noise at the input. The DC offset here could have a small component of low frequency noise on it. To test that, I have on the pre-amplifier increased the capacitor here, tantalum 10 microfarads to 200 microfarads on the gate of the input stage, 6 times J310. Now that didn't have any effect at all that I could observe. So I tried on the output of the preamplifier with an RC filter that would remove frequencies well below 50 Hz. Just a resistor and an electrolytic capacitor. This made a difference that I can see. 50 Hz is here, and the level is about minus 157. And the difference between phase noise and amplitude noise is small. And what I observed before was minus 156. So I will expand the scale here and make a more accurate reading. The AM noise now is minus 157.1 and the phase noise about minus 156.8 or so. A little bit hard to see because the 50 Hz spur is so strong on the phase noise. By filtering the DC on the input of the power amplifier is about 1 decibel, a little bit below, 0.6 perhaps. And it's these two lines that show the difference. And it's about the same for all frequency separations. It looks a little bit larger here at 400 Hz, and that is probably because I have now collected many more averages, and at 400 Hz offset this makes perhaps a small difference. But I'm not sure on that. On the other hand, for the phase noise, the difference is much smaller, maybe insignificant, 0.2 decibels or 0.1 decibel. So anyway, having a separate voltage divider properly decoupled for low frequencies to provide the DC bias for the power amplifier will be a good idea. I have now arranged a separate voltage divider for the base voltage of the power amplifier, and this gives a small improvement. I have been running for a little more than 4 hours, and here is what it looks like. The upper trace is the yellow, which is phase noise. So the amplitude noise is at minus 160 at 50 Hz. And I click to the other screens. Here we can see that phase noise, the imaginary part, is down at minus 175, so it doesn't contribute. And all the way up to 400 Hz, I have waited long enough. And for the AM noise it looks similar, and also here. So I can use these curves to evaluate and write in my table. With the preamplifier included, the noise is even lower. And I think this is because the impedance on 10 MHz is also very low now. It comes close to the Wenzel. Here I see 159.9. The Wenzel was at minus 162. So that's only 2 decibels. And that's 50 Hertz. At 100 Hertz, the Wenzel was minus 165. And now I see minus 165.3. 150 Hertz, 167.9. And the Wenzel 165.8. So now my selective amplifier oscillator is similar to the Wenzel at 100 Hertz, and it's a little bit worse at 50 Hertz, but it's much better at higher frequency separations. At 300 Hertz, for example, 166 for the Wenzel and 172 for my unit. That's 6 decibels. Phase noise is not quite as impressive. I see now minus 154.5, while the Wenzel is minus 157. So that's 3 decibels. And if I go upwards, the Wenzel is 160 at 100 Hertz. And my unit is minus 161.7. So it's also better at 100 Hertz. And if I look at the phase noise at, let's say, 300 Hertz, the Wenzel minus 163.6, and now I see minus 171.8. That's much better. Minus. So now I will run the unit as an oscillator to see what happens. Here is what I see after nearly 20 hours, and that is 258,000 averages. It looks pretty good. I will look at the detailed information. Here is for the phase noise, and it's clear that in this region above about 500 Hertz, the noise from the center frequency, that means DC on the audio card or the ADC converters, you can see here very close to 0, that is 700 Hertz from the carrier. There is no correlation advantage. It means the noise I see is correlated between the channels. And the phase angle is somewhere around 45 degrees. It means I see a strong signal in the imaginary part, and as it happens in the real part it's negative, so it comes blue. And this slopes fairly rapidly, and at this point here the positive and the negative component that goes into the real part happen to cancel each other. So I read artificially minus 190. That is of course not a true reading. So what I do is to extrapolate this curve down like that, and that means that at maybe 400 Hertz the contribution from the center is negligible. But I cannot read from this graph over 400 Hertz. And looking at the shape here, when the curve starts to bend down, maybe this isn't real. So at 400 Hertz, that is absolutely the highest, and probably, or perhaps there is an error of 1 dB or so. So I can reach minus 175 for the phase noise at 400 Hz. And here is the AM noise. It is more favorable. It means that the contribution from the center is smaller, and at 400 Hz it doesn't have any effect on what I can read. So what I see here is minus 172.5 approximately. So I compare the unit running it as an oscillator and as an amplifier. And I look first at the phase noise here, and I find that as an oscillator it is not quite as good at 50 Hz, but at 100 Hz it's the same, and at higher offsets the oscillator is better than the amplifier. Because the filter is removing phase noise that is present in the Wenzel oscillator. But looking at the AM noise, at close range it is degraded by about 1 dB, but at wider ranges it's degraded by 2 dB. Here is 300 Hz, and about 1 dB here. And I should expect an improvement rather than a degradation. I think perhaps that the amplifier, it uses positive feedback, and feeding it with the output of itself, which should be minus 173, that should give a better result than feeding it from the Wenzel, which was 167. But it works the other way. So this is probably because of positive feedback. There is positive feedback in this oscillator, as in all oscillators. Small variations in the amplitude might be amplified, which points to an insufficient limitation in the crossed diodes used for amplitude stabilization. I have removed this resistor here and also shorted this resistor. This makes the limiting a little bit harder by these diodes. I mean, the transfer curve from amplitude here to amplitude here becomes sharper like that rather than like so. As a result, the amplitude is a little bit lower. And indeed, that makes a small difference. It is more obvious now than before that the result here, minus 180, cannot be correct, minus 185 for the phase noise. So I click at the details, and yes, at this point we have the negative contribution from the DC that cancels the positive from the oscillator and creates 0, roughly. I cannot measure accurately above about 350 Hz. I need a 10 dB separation between this curve, the real part, and the imaginary part to trust what I see. This is phase noise, and here is amplitude noise. Amplitude noise should be okay up to about 400 Hz. So I evaluate what I have from these curves. After the modification, performance is clearly better. This is AM noise, 50 Hz, and all the way up to 400 Hz. It's about 2 dB. For phase noise, there is also an improvement. It is now minus 153.8 at 50 Hz. Not too far from the Wenzel at minus 157.2, about 3 dB. At 100 Hz the Wenzel is minus 160, but my unit is nearly 3 dB better now. And with higher frequency offsets the difference becomes bigger. At 350 Hz I see minus 173.7, while the Wenzel is at minus 164. That's a difference of about 10 dB at 350 Hz. And at 400 Hz I cannot measure any longer because the DC interference is too strong here. Here is the amplifier from the input to the amplitude limited output, but at a low level where there is no limitation. The gain is 1.8 dB only, so the diodes are clipping by 1.8 dB when it's oscillating. The input impedance is 49.3 ohms at the peak, and the Q is 113,000. I will try to modify a little bit to bring up the gain. At the peak, the phase angle is here, very close to 0. So tuning is correct. I have increased the input resistor from 100 to 120 ohms and retuned these capacitors. That increases the gain by about 1 dB, but the impedance is now also very close to 50 ohms. I have removed this winding. Actually it was only one turn. This gives a little more signal into the power amplifier and that probably degrades performance a little bit at very wide frequency separations, where a little more noise from the wideband white noise from the pre-amplifier goes into the power amplifier. But the more signal here means the amplitude limitation becomes stiffer here. And that's what I want for the close range, AM noise. After 28.5 hours, 377,000 averages, this is what I see. 50 Hz, phase noise about 156, AM noise about minus 163. And then it goes like this. Here I have a problem at a little bit above 400 Hz. I have moved the 700 Hz a little bit higher. You can see it is maybe 710, 715. And that means that overtones from 50 Hz, 50, 100, 150, 200, 250 is here. And this is the sidebands from the DC. Means 50, 150, 250, 350 from the zero peak. So I have moved the problem with the sideband, with the noise from this DC a little bit further up. So when looking now, I go for the complete information. I can see that here is some kind of spur. There is a peak here. So I have a problematic situation. The spur is negative in sign. So, but it looks like I can trust values up to 400 Hz. It's this little peak where I see minus 175 for the phase noise. And for AM noise, here, it looks a little bit odd that it bends here, but on the other hand, it seems unlikely that the negative signal from the center can contribute at this point. But there is some spur here, and maybe there is also here something, I don't know. Anyway, I have a better result now, and I will stay with this and investigate other aspects of this oscillator. But first I will take down all the numbers from this measurement. At 50 Hz, the phase noise is minus 156.1. While the Wenzel was minus 157.2. That's just a single dB. And the amplitude noise is minus 162 at 50 Hz. And that is the same that I was seeing with the Wenzel oscillator. Remember, it's not a cheap device, that one. Now I want to look at a closer range than this. To do that, I have to investigate the limitations of my system. This box controls the phase locking between the two oscillators used for the direct conversion receivers. This knob here steps the time constant in steps of 3. 3, 9. So now the PLL is far more rapid. That means that phase modulation that is present on one oscillator will also be present on the other up to some corner frequency of that low-pass filter that is in the PLL loop. So I look for phase noise, and now I clear the display and start to see in what way has performance changed as seen by this system. Now this is 12 hours later, or nearly 13. What I see is quite different from before. Phase noise seems much stronger. It's about 150 dBc per hertz at 50 hertz. But the amplitude noise is similar to before. I look at the details of phase noise here, and we can see that the sign of the real part is negative here. The imaginary part is even stronger than the real part. PLL means that one oscillator is following the other. At very small frequency offsets, they should be identical and there should be no correlation advantage at all. That's what we are approaching here, very close. And then at higher frequencies, the RC link is doing more and more filtering. And we can see how this curve here goes down into the noise at minus 180, somewhere around 200 Hertz. This is with a time constant, the smallest one that I have. And I said before they are a factor of 3 for each step on my switch. Actually, I have resistors 1, 3.3, 10, 33, 100 and 330. So now I am at the value 1 and the biggest is 300 times bigger. So the point here will go from 200 Hertz down to below 1 Hertz, where the result starts to be unreliable. So the PLL is slow enough to allow me to go down to about 1 Hertz, and probably a little bit below that also. I have now restored the normal setting, and you can see here the white range is narrower. So I can see already in the direct spectrum there is a difference. And you can see that here, this average jumped down. And if I clear the screen, like this, we can see pretty rapidly that things are again as they were before I made this change on the time constant. The phase detectors used to produce this FM demodulated signal, which you see the spectrum of in this analyzer window. That FM detector is an IQ demodulator. The carrier is extracted through this narrow filter with a bandwidth in the order of 10 Hz. If I make this filter much wider, I can do that by changing parameters. Like this. Now this filter is about 200 Hz, which means that frequencies up to 100 Hz will be present in the reference signal I have, and that should remove phase modulation below about 100 Hz. So I can clear again the spectrum here and see if I can see that. And I don't have to look at the correlation. I just set a larger number of averages here, and then I can see the curve here, the detected FM signal. It has very deep minima at 100 Hz and at about 50 Hz. And I cannot say that I really understand it, but up to about 150 Hz I see some oddities. So it means that if I want to go to 1 Hz, I should set a filter bandwidth here of about 1 Hz. So I changed the first FFT bandwidth from 10 Hz to, let's say, 2 Hz. And I still have the window power 9, which means a flat response with Gaussian error functions as how it falls off. And then I reduce here by more. Let's change it to 5 to make the baseband bandwidth smaller. Now the baseband bandwidth is about 1 Hz. I have increased the number of points in the baseband FFT to 14, 2 to power 14. And this makes the spectra here slow, and I have to wait a long time, but I will be able to read down to about 10 Hz offset, maybe 5 Hz. After nearly 3.5 hours, statistics is good enough for me to draw some conclusions. Here, below maybe 8 Hz, there is some drastic change in the phase noise that doesn't look quite right, and it clears what it means when I click for the details on phase modulation. And now things are slow. I have to wait for the curve to reappear here. And as you can see, the real part of the correlation average is blue, means it is negative. And the imaginary part goes up and becomes very strong. This means there is a lot of correlated noise between the channels, and the phase of it is incorrect. This is an artifact of some kind, and it's not the phase locking. It looks like it would be that, but I have verified that the PLL time constant is good enough all the way down to 1 Hz. So I suspect that this is pulling between the oscillators. They go to mixers and there may be some leakage some way, and I will look into that in a separate video. Anyway, down to about here, that is 10 Hertz, the result is probably correct. I can evaluate phase noise here at 50 Hertz. I had before minus 156.1, and that looks perfectly in agreement with what I see here. And at 100 Hertz, the old value is minus 164, and that is where I have the mouse now. So it looks also like as before. I will take down the values down to 10 Hertz from this measurement, and also for the amplitude part, which comes soon. I have clicked for A and I have to wait. Here we have at 50 Hertz it is minus 162 approximately. I had noted 162.0 before. And here I don't see this artifact from frequency pulling, but something happens below 4 Hertz or so, I think. This will be a later study when I have fixed, if I can do that, the phase detector or the PLL between the two oscillators, or the coupling between them, or whatever causes the error on the phase noise measurement below 10 Hertz. I do the valuation like this. Here is 20 Hertz. The camera doesn't show the correct because it has a parallax problem. There is a glass between the screen and where I hold the instrument. But from my eyes it is now precisely 20 Hertz. And then I look, where is the curve? Well, about here. And from the position of my eyes when I am perpendicular to the screen, I found this position to be 144.3. And of course there is some uncertainty because I have to try to make a straight line somewhere here in the noise. It would be more appropriate to take the smoothed curve in the linear power scale and then draw it in the dB scale. 10 Hertz comes here at minus 136.5, with a significant uncertainty, of course. I have now connected the Wenzel oscillator and switched off my own old home-built one to not have any leakage from it. And I have to wait for this to stabilize, and maybe half an hour or so. With 20,000 averages, the correlation advantage is square root of 20,000. That's 21.5 dB. It's about, well, not quite. Something like this. So going from the raw data to the detected FM modulation, I find the imaginary part at this 21.5 dB down. And then I can follow it, as you can see here, but at this point, and that is above 10 Hertz, the correlation advantage isn't big enough. And here, the random noise of the receiver itself, that sideband noise of my local oscillators, is as big as the expected correlation signal, or even bigger. So it adds at random, sometimes negative. And then at a little bit closer range, I have this problem that the oscillators are correlated somehow. So it is very slow. It's now 12 hours, and I cannot read the performance at 20 hertz even with the reasonable accuracy. So I would change the settings to make the resolution significantly lower. I have decreased the transform size by a factor of 4 and increased the frequency scale by a factor of 4. So peaks are much wider, and the time it takes to collect many enough averages is shorter by a factor of 4. So I have now waited for 13 hours, and the signal to noise ratio, I record the imaginary part here as the noise, and here is the signal. That means the noise from my oscillator and this spur. So I can read now better information than I had before on this oscillator, because then I didn't wait more than, I think it was 2 hours or so. But I can see also here down to maybe 20 hertz, and below that there is some problem with my system, these negative values, and they contribute, and I can see on the imaginary part something is wrong here. But this is probably a representative for the unit, and I think this is more or less reliable, and this is certainly okay at 40 hertz. So I expand this scale and read more accurately the numbers. And here is the amplitude noise. It is a little bit lower than before, but this is also a much longer time. Here is what I have found. This curve, that is the amplitude noise of my amplifier oscillator from an old measurement, and here is what I have found after the modifications. So the improvement is in the order of 15 decibels at 20 hertz. The phase noise, the round dots, is also improved, but not so much at a close range. A little bit more at a wide range, well, 250 hertz here. It goes down to this point. And at this range, the amplitude noise is improved from here to here. The measurements of the Wenzel are the red points, circles for the phase noise, and rectangles for the amplitude noise. You can see here phase noise, amplitude noise, these curves. The black crosses are the measurements I have done now. The ones at the wider bandwidth with a larger FFT fit very well on the old results, while the result I got now, the last measurement on a smaller transform size, indicate a 3 decibels better performance for the amplitude noise. I don't know the reason for that. Something is perhaps not quite right with the phase adjustment for the IQ detector, making it work better when the transform is smaller. I don't know. Anyway, the unit is much better, and I have shown what errors, design errors, I have discovered by using it as an amplifier, and that is the message of this video.